Hello everyone and welcome to today's webinar. Our topic is a malicious insider's guide to compromising encrypted networks. My name is Jonathan Lewis and I'm the Director of Product Marketing at SSH Communications Security. The issue of malicious insider attacks is really a little broader than specifically attacks perpetrated by insiders. It also includes the use of insider access by external actors to basically leverage privileged access to remove information from an organization, and we see this taking place specifically around the issues of advanced persistent threats and social engineering attacks and the like. So let's get started. First of all, we need to take a quick look at the cost of data breaches, because that's really the primary purpose of most insider attacks. And we see the data breaches that are publicized and make the press are highly costly. They run in the tens of millions of dollars and hundreds of millions of dollars in some cases. And of course, for smaller organizations, the absolute dollar costs are lower, but the impact on a smaller organization can be even greater in terms of its ability to absorb the consequences of these types of attacks. And central to the attacks is the issue of a privileged channel risk. And this is information on the graphic here of, from the Verizon 2012 Data Breach Investigations Report. And I encourage you to find that report and read its contents. It has a lot of good information in it. But a couple of things from the report that I wanted to highlight is that a lot of insider crimes go unreported for both because the organization may be unaware that the attacks actually took place, or because for reasons of not wanting to have negative publicity, they decide to handle it internally and not deal with it through law enforcement. And another issue is that partners lack security practices, and poor governance can actually spill over in terms of risk to the enterprises that are using a partner's services, or perhaps implemented some supply chain integration. And so the security of a partner network becomes an important factor in terms of assuring data protection and security for the enterprise itself. And this is an issue which is growing because of the increased reliance on external business partners and the more automation and supply chain integration that enterprises are taking advantage of. Another report which is worth referring to is the annual cost of cybercrime study conducted by the Ponemon Institute, and the information on this slide is actually from their 2012 report. And what they found is that the most costly cyber crimes are, in fact, caused by malicious insiders, as well as costly crimes from denial of service and web-based attacks. And in terms of the cost components, the loss of information represents the highest external cost. So if, for example, medical records or credit card information, social security numbers, etc., if those are lost, the recovery costs from basically resetting all that information, is making sure people's credits is okay and haven't been affected, and so on and so forth. All these add up in terms of external costs. The other element which contributes to cost is the amount of time it takes to resolve an attack. And that is really part of the issue around insider access, because they tend to be difficult to detect. They also tend to take a long time to resolve, and of those, that contributes to the overall costliness of these forms of attack. If we look at what's really contributing to the difficulty in both detecting, stopping, and preventing these types of attacks, it's really central to that is the issue of encryption, which is kind of a double-edged sword in these scenarios. There are obviously privileged communications that need to take place, and they need to be secured. They need to be assured of integrity and confidentiality. And of course, encryption provides for that. So whether that's employees accessing confidential information, contractors, people using bring your own device, and specifically M2M processes. And by what I mean by that are the machine-to-machine processes that often support a lot of automation. So, for example, a machine-to-machine process may consist of a web-based transaction which triggers automated access to a back-end database where there's credit card information. So all of this information needs to be secured through encryption, but at the same time, if the layered defenses that have been put in place to protect the information in the first place is not capable of inspecting that traffic, that traffic is largely unmonitored and uninspected, and so the layered defenses such as intrusion prevention systems, firewalls, data loss prevention, and event management systems are effectively not able to do their job in terms of protecting information which is brought in and out of the network through encrypted access. In terms of protocols, one of the protocols of choice for providing secure authentication and then an encrypted channel for communication is Secure Shell. It's really the tool of choice for trusted processes and insiders. So that comprises both machine-to-machine and person-to-machine types of communications. And that would include systems administrators, contractors, IT outsourcing, bulk file transfers in terms of automated processes and other machine-to-machine processes that are perhaps very transactional oriented. And what we see from a recent survey conducted by Forrester Consulting is that over 90% of enterprises are using Secure Shell, and for the most part, they are using it for critical or highly important business processes. So Secure Shell in the enterprise, the good is that, of course, it's providing confidentiality for data transfers, enabling secure systems administration, and providing for secure process automation, which is that machine-to-machine function I just talked about. However, on the negative side, the Secure Shell authentication keys can be an attack vector for both malicious insiders as well as external threats seeking to use those keys as a way to get into a network and remove data. And that's specifically how the keys can be misused, which is to obscure data theft or to conduct other unauthorized activities. Let's take a little closer look at the Secure Shell authentication keys themselves. Secure Shell authentication keys consist of a key pair. It's a basic asymmetric encryption, and so one side is the private key and the other side is the public key. And the private key can also be referred to as the identity key, and it validates the identity of the person or processing requesting a login. So that can be a machine-to-machine process that needs access to a remote system, or a systems administrator needing to gain access to an account on a server. They may need root account access, or they may need access into a service account, for example. Now, the public key also can be called the authorized key, and that essentially establishes what level of access is granted to the holder of the private or identity key. So if the corresponding public key corresponding to a private key is located as the authorized key in the root account on a server, then anyone with the private key can log in as root on that server. And the keys, as I mentioned, are used for automated processes, and one of the reasons for that is they do not require an interactive session to perform the authentication. So no person is needed to type in a credential. The authorization request is fully automated. But of course, keys can be used for interactive connections as well. And normally for an interactive type session where there is an end user available to type in credentials, the private key would be passphrase protected. Although what we see in practice is that not all systems administrators do passphrase protect their private keys. The keys themselves are basically simple text files, and they're located in a directory on the client and server machine. So the client is the one requesting login into a server, and so the client has the private key and the server has the public key. And in both cases, they are just plain text files. As I said, the private key may or may not be encrypted through a passphrase, but in any case, the private key can be moved about and copied from one place to another, and that is an actual source of vulnerability with respect to insider access. So let's take a look at a few scenarios where the keys can be potentially misused. In this instance, Bob might be a systems administrator who has authorized access to a production server. He may be given root access. And once he is logged in as root, he can, in fact, add another key to that system on the server. So on his workstation, he can generate a private and public key pair and copy that public key over to the root account on the production server. And now he has effectively a back door into that server because the public key is effectively unknown to the rest of the organization. It was placed there in an unmonitored and unaudited fashion. He can take a copy of his private key and move it to his workstation at home. And now there's another source of access into the production environment that is not authorized. Bob can also decide to give a copy of his private key to another person, maybe a coworker, so that person can do some work on his behalf without having to go through administrative issues, so he might want to do that just for convenience purposes. And finally, if Bob's computer is hacked, that private key can be stolen by the hacker, and now the hacker has access to the production environment. So this is a risk scenario that can affect any system that's running a secure shell server. So that would include not only Linux and Unix systems, but also a lot of Windows systems and mainframes as well. Many organizations, in fact, may not allow direct root access by administrators, such as the previous scenario indicated, and they require that administrators log in through a jump host. So an administrator provides their personal credentials to a jump host, and the jump host does a proxy authentication on that user's behalf into a Unix environment with different credentials. However, once that user is logged in, they can create a private and public key pair, just as we saw in the previous slide, and then add that public key into the server environment. And now they have a backdoor, and in subsequent logins, they don't have to go through that jump host, and those logins would be unauthorized and unmonitored. In the mainframe environment, is not all that different. The users are normally authenticated, and their access is recorded through RACF or another access control facility into the mainframe environment. But in the Unix system services side of ZOS, a user can add a key, again generating a public and private key pair and adding that public key to Unix system services, and from there gain access into the MVS side without having to go through RACF authentication and authorization. And of course, that private key can be shared with others, and so the access into the mainframe environment can actually be relatively widespread without anyone really knowing about it. There's also an issue of transitive trust, and in this example, we would have a systems administrator who has a trust relationship into production server 1 so they can do their administrative work. And at the same time, production server 1 has a trust relationship with production server 2 in support of some automated process, perhaps supporting a transaction system. What that really results is that systems administrator A can leverage these trust relationships to be able to do file transfers, for example, on production server 2, leveraging the access that they have into production server 1 and then the authorizations that server 1 has into server 2. And what we see that is a transitive trust can propagate quite widely within an organization primarily because there is such a reliance on machine-to-machine processes as well as the various trust relationships for administrative purposes. So what we see is that a user who maybe they lose their private key is stolen or lost or whatever, and that provides access to one system, that access can be leveraged to hop around the network. And so if the stolen key is in the hands of a malicious user, that user has the capability of kind of traversing a lot of the server environment. And the final issue that we're going to take a quick look at is the collapse of separation of duties, and that can be leveraged by malicious insiders. What most organizations think they have is a separation of duties between production and test environments. So production users, of course, have access to the production environment, and developers only to test. And that's not only sort of a sound security practice, it's also a requirement for through most security mandates, such as PCI DSS. What, in fact, many organizations do have is a breakdown of that separation of duties. And what can cause that breakdown is when developers have their authorization keys in the test environment and software images are moved into production, unless the developers were security aware or there are procedures and processes to manage that. The keys can be transferred from test into production, and that would then give developer access into production environments. And in the case of machine-to-machine processes, if the test environment is setting up to develop and test applications that provide for automated transfers server to server, and the images get moved into production, now systems in the test environment have access into production. So how can this be leveraged, leveraging access and encryption to remove data? The step one, of course, is gaining access to the server environment. And as what we saw in the last several instances is that there's a number of ways in which malicious insiders can gain greater access into the environment and do so in an unmonitored fashion. Or in fact, it could be a scenario where there's an external actor that gets hold of the private keys that are authorized on these systems, and then they have access. And once given that access, the malicious insider can extract information through an encrypted tunnel. So they have the ability to create a secure connection and then leverage that connection to remove data all encrypted and bypass the security controls that are put there to monitor activity on the network. And we see that these threats are real. There's a few examples here on this slide I'll just touch on briefly. The example up in the upper left of the former HostGator employee charged with rooting 2,700 servers is really very similar to the made-up example of Bob putting their private keys on a server in an unmonitored way. I should say he created a key pair and added public keys to those servers. In the case of this HostGator employee, this was more or less what this person was doing, except he did that 2,700 times and, of course, had extremely severe access into the network and was actually stopped before he was able to do some damage, but it became public because it was a serious enough offense that the authorities were notified and the person was arrested. In the case of GitHub, it's more an example of the inadvertent issues that I talked about with developers not necessarily being security aware and moving images with authorizations from one environment to another. And this was happening on the software sharing site GitHub, where developers were leaving authorizations into software, and if picked up and used by others, would therefore have backdoors into their systems. And there's an example on FreeBSD of how this was being done deliberately, where, again, BSD would be picked up by users, by enterprises, using that operating system for their server environment, and then there would be backdoors baked into the images that they were and the builds that they were putting in their environments. And the last example here is about an APT called Mask, which was just publicized within the last several weeks. It was brought to light by Kaspersky, and if you go to Kaspersky's website, there's a lot of very useful and interesting information about this particular APT. And what was interesting within this particular context of our topic is the APT was doing two things. One was it was, of course, scanning any system that that the malware was had managed to infect, with looking for, of course, any valuable information, all types of document files, etc., and also for secure shell keys, because it was using this issue of hopping about the network using the string of authorizations to get onto more systems, look for more information, and basically become pervasive across the environment. And then the last element that this APT was doing was extracting the information to an external command and control server through an encrypted tunnel. In this particular case, they were using SSL, so it's an example of using a couple of different encryption protocols to gain access into the environment, hop around the environment, infect more machines, and then remove the information undetected. Some of the takeaways from APTs in general and the Mask in particular is that really there's no amount of end-user training and education to completely safeguard an institution from being infected by an advanced persistent threat. A good training program can reduce the success rate of attempts at phishing, etc., but it is a known fact that someone always clicks, so eventually the malware will get onto the network. And once in the network, APTs can be virtually undetectable. And the Mask is a good example of that, because it took something like 7 years for this particular APT to become revealed, and it was subsequently found that hundreds of organizations around the world have been infected by it, and there may be others that are infected but have not been discovered yet. Perimeter defenses are also largely incapable of preventing an APT from entering the network because typically they're essentially done under the guise of an authorized activity. And then once they're there, very difficult for perimeter defenses to stop them from communicating with command and control. And to a large extent, that is due to the issue of encryption. So we have an issue which is basically summed up as security versus visibility. There are legitimate requirements for encrypted connections, both internal to within a network, from inside a network to an external location, and external to internal. But at the same time, these communications cannot be totally opaque to their defenses. There needs to be a way to trace and audit the user's commands and activities, and needs to be a way to inspect and analyze the incoming and outgoing data flows. Without that, you really cannot adequately protect the valuable resources of the enterprise. So what we see as a requirement is what we're calling content-aware access management. And by that we mean the ability to not only authorize the connections through central directory services, but apply stricter policy controls to those connections and monitor and record what takes place during the sessions themselves. So what our product offering content-aware access management is CryptoAuditor. I have another slide that goes into a little more detail about the product itself. But in terms of process and what it actually does in the network, it starts with an authentication. And in this case, CryptoAuditor intercepts an authentication request, proxies that to a central directory, such as Active Directory, and gets authentication and authorization information back from the directory. And from that, the secure shell connection would normally be authorized. But the nature of secure shell is that you can really do a lot with a secure shell connection. It's sort of an all-purpose type of communication vehicle that allows you to run almost any application encrypted inside that connection. And so there needs to be some policy control to limit the functionality of that secure shell connection to the specific functions that are authorized either from an employee to server farms perspective or contractor or a machine-to-machine process perspective. So that's a policy enforcement aspect, is given the identity of this connection, what is that person or process supposed to be doing? If it's a Windows administrator, then they should not be running secure file transfer protocol or running port forwarding applications. They should perhaps only be doing RDP, and that would be a policy enforced for that particular connection. If it's a machine-to-machine process, there would be no need for remote desktop protocol or application tunneling, but perhaps SFTP would be authorized. And then finally, there's the issue of enabling the layered defenses. Once that secure connection is authorized and the policies are being applied to it, you still want to make sure that there's continuous monitoring in place to make sure that no unauthorized activities are taking place within what is allowed to that session. So continuous monitoring means feeding information to intrusion prevention, data loss prevention, event management systems, and creating an audit trail. So there's the component of both real-time defense here, as well as having an audit trail that would, in the event there is some kind of a breach, provide a quick means of investigating what happened and shortening that time to resolve the problem. CryptoAuditor does provide that. It offers a deep protocol inspection for secure shell and its sub-protocols, a remote desktop protocol, and so there's that ability to not only inspect but apply policy control to these connections. It offers full session visibility and recording, and real-time indexing, alerts, and enforcement. And what we mean by that is that in a real-time basis, alerts can be generated, or if something unauthorized takes place, such as an attempt to remove information with credit card data in it, it can shut down the connection. And it does that through enabling the layered defenses such as data loss and IPS. So it can feed information to these systems and then get real-time information back that would allow it to block or to block a session or send a message to the end user letting them know that they shouldn't be doing what they're doing. And finally, there's a distributed deployment and central management. What the CryptoAuditor can be deployed in distributed fashion, so the monitoring devices that we call the CryptoAuditor Hound can be distributed to the key points in the network with a central management system gathering the information and storing it in the CryptoAuditor vault. So there's central management, central storage with distributed monitoring and enforcement. And finally, the product itself is available in a hardware appliance or can be deployed as a virtual appliance. So it can be installed in your virtual environments without having more hardware to your network. Overall, there's growing awareness of these issues, not only in the security technology press, but also in the business and wider presses as well. So we see American Banker, Forbes, Red Herring, etc. These publications are kind of picking up on the importance of these issues, and it's not just sort of something that's only where the awareness is only within the security professionals. A little bit about our company, SSH Communications Security. We are the inventors of the Secure Shell Protocol. Our founder and CEO, Tatu Bionen, invented the protocol in the mid-90s and has been an author and contributor to over 90 RFCs. So both he and the heritage of the company is highly knowledgeable and really are the experts on Secure Shell. And we work with a lot of large customers. Large enterprises comprise most of our customer base. And we're pleased and honored, of course, to be working with 7 out of the top 10 Fortune 500 and the top banks. It's very gratifying that we've earned their trust. And of course, we learn from our customers, which of course informs our product decisions and the kinds of solutions that we're offering. In terms of our portfolio, our client server line of Secure Shell products, Tectia SSH, is really providing transaction security. And what we offer with Tectia SSH is functionality and oftentimes support that is not always available with open source implementations, and that's why it's become quite popular, particularly with larger enterprises. Moving up the stack, CryptoAuditor provides content-aware access management for these transactions. So you have either open source or Tectia-based transactions which are secured through encryption, and CryptoAuditor can now provide access management and content awareness to those sessions to effectively resolve the insider and malicious outsider attack scenarios that we talked about previous in this webinar. And then lastly, Universal SSH Key Manager is an overall identity and management and governance platform for this infrastructure. With the proliferation of user keys, Secure Shell, private public key pairs across the environment, we see enterprises with over 1 million keys. These really do need to be managed in order to have proper onboarding, offboarding, etc. of these identities as users and machine-to-machine processes are spun up and spun down within the organization. Some of our customers, we work with most of the major industry verticals, and that's all I have for today. I want to thank you for attending. If you'd like to ask a question or contact me, my email is up on the screen here, or just come to our website. We're easy to reach, and we'd love to talk to you. So thanks for attending, and hope to talk to you again at our next webinar. Bye for now.